for you guys to catch up, and I expect you guys to run Simulinks in parallel to what I'm telling, and make things do the exact things what I'm doing here, so that if you uh, face any issues, we'll resolve it now itself. Okay, so I'll start with sharing my screen, and if you guys have any doubt, please interrupt me in middle, or maybe raise hands. So can one of you volunteer to tell me if there are some raised hands, because I may not be able to see the team's page always. So any volunteers for that? Rajpal, can you help me with that? Or
Sure, I'll volunteer then, no issues.
okay, yeah, thanks. So I'll start with starting the app. So hope you guys have installed the libraries in the order of in the right order what Rajpal sent in the group. So if you have done that, you'll see there is a button here called Simulink, Start Simulink. We'll start that. So like there are some examples as well of different models and different basically uh, things of how, like, there are some different models like simulation of a bouncing ball, or modeling of some automatic transmission, or hydraulic cylinder simulation, and all those things. But since we just want to get you guys started, so we'll start with a blank model straight away. And and yeah, so generally Simulink um, page looks something like this. And some of the, like, there is a library browser which has all the elements. So we generally use Simulink to model few things, and since we don't want to type each and everything, it is just easier for us to just take some building blocks and then compile it in a flow chart way, and then visualize the results. So Simulink is a very good uh, in that sense. Simulink help us to build a model very quickly from the mathematics which we already have, and in a very quite good visual way of flow charts of what we generally see in some controls lectures and all those things. So basically we have this library browser which has all the building blocks. So if you see the math operations, you have this adding, absolute, dot product, gains, right? Product, all these things, which we generally use while modeling our Simulink models. Along with that, we have all the other operations, right? So just for starter, I'll maybe start with a small. So we'll take a signal, and then maybe amplify it, and uh, and then see the results actually, right? So so and yeah, there is another way that you can actually bring these models here. So if you double tap the page that we have here, you get a search option. So I'll directly start with a simple function, sine wave function, right? So sine wave function looks something like this. Sine signal, right? And then maybe I'll use a gain block. Or yeah, so basically you can actually, if you double tap this block, you can change the amplitude So currently the default value is 1, right? So we can change it to maybe say 2 or maybe 3, right? And then apply and then click OK. Then maybe we can actually have a gain block, right? So again, I'll again double tap on the screen directly, and then search for gain and click this. So you'll get a triangular shaped block, something like this, with again the default value is 1. So you again have to double tap it and then change the gain to whatever gain you want. So I'll again put 3 here and then hit apply and OK. So this is basically gain of value 3. So yeah, I'll do this. And then I can actually, if you see, I can connect these two blocks in with the direction of uh, in the direction of say the movement of the signal. So signal moves from this sine wave generator to the gain block. So you can directly double tap this arrow, which the blue arrow which already comes, and if you double tap it, you'll get this good line. Yeah. So is there any doubts? Everyone okay till now? I hope everyone is like following me till now. Okay. So yeah, I do have this system right now. So how do I measure my output signals? So we have something known as scope. So if I again double tap it and search for scope, I'll get something like this. Uh, So basically, what a scope does is it will help us measure the output signals as any kind of signals that we already have, right? And we can give some certain inputs which we want to, whose output we want to see actually. So again, if I bring my cursor close to this side of the scope, there it will show me a plus sign along with that, if you are able to see it. So if I tap this plus sign, I'll get another input port if in this. So now I have two input ports, and I'll arrange it in a way so that I get a blue line again. And so what I want to measure is this the signal of this output as well as my sine signal which I sent earlier, right? So I'll just all you have to do is bring like there is a arrow which is coming here. So I'll again delete it and show you guys. So if you see this second port, all you have to do is drag drag this arrow from here and put it at the point where you want to measure the signal. So currently we want to measure the input signal as well as the output signal to this gain block and see what are the outputs actually. So like if you see the scope, if you double tap the scope button, you'll see the output. But since we haven't simulated it yet, the output and the input all are 0 right now. So we'll have to run this uh, simulation and see what are the results. So if you see, we have um, we have this yellow signal which we have for the output of the gain, which is almost 3 times as compared to the as compared to the input sine wave of amplitude 3 which we had, right? uh, so yeah, if you guys can see it more clearly, we have this output sine wave and this is the input sine wave which we which we had to the uh, in the gain block basically. So I hope you guys are able to follow it till now. So are there any doubts as of now? Is everyone able to follow what I'm telling? Okay, okay. So yeah, please do
Yeah.
interrupt me in middle if you have any doubts. Okay.
So
So
this signal block that we have, uh, the sign signal that we have chosen,
sorry, sir.
the signal block, the sign signal that we have chosen.
Yes, sir.
Yeah. So could you elaborate a little bit on the properties of the sine wave that we have chosen? What is the frequency? What is the amplitude? So on and so forth. Right.
Yeah. So yeah,
So
yeah, yes, yes,
yeah.
sir. So if you double tap the block, sine wave block, you will be able to change the amplitude of the signal as well as the frequency, phase, and all those things. So currently we have an amplitude of 3 right now, and a frequency of 1 radian per second as of now. So if I change my frequencies to say zero point 0.5, I'll again see the I'll again run the simulation. So you can run the simulation from this button as well as from this button in the scope. So you
Yeah.
see that we are able to get the like the sine wave is elongated by double actually. Since we reduce the frequency to half, right? And also I can increase the stop time. So currently, if you see, we have this stop time at 10 seconds. I'll maybe increase it to 30 and run it again. So yeah, you're able to see that we have
So
a
we
broader
have,
span of 30 seconds.
yeah, we have changed the amplitude. We have reduced the amplitude. The frequency is appears to be the same. So what I'm more interested in is in the sample time. So what if we keep a sample time other than zero?
So you have a sample time of zero point 0.1 and then apply.
So,
Okay.
so what change will it make?
So yeah, if you can see that if I change the sample time to zero point 0.1 and maybe I'll increase the, so you can see that there are some steps, right? So it is so the graph is not smoother now.
So it's a sampled signal now.
Yeah, so it is taking signals at an interval of zero point 0.1 seconds actually.
Okay,
So
fine.
that is why we have this zigzaggy kind of like a step kind of signal as of now. So if you
So,
can see, like the signals are taken, like the values of the signals are taken at an interval of zero point 0.1 seconds actually.
so if we want to have a continuous signal, we have to use a sample time of zero. But the output doesn't seem to be affected. Or is the output also affected? I'm not able. Yes, it is. Yeah.
Yes, yes. So basically, this is the input. The blue one is the input signal,
Yeah. Yeah.
and the output is
Yeah.
this yellow one.
Yeah, I can see the change in the output as well. You
Yeah,
need
yeah.
a little bit. You just need to zoom it a little bit. Please carry on. So
Okay.
uh, the students who are actually who have joined. So if you have any question of any any doubt whatsoever, please ask. This is the right forum to ask these questions, and Rajpal and Manan will try their best to explain whatever whatever queries you may have. Please go ahead. Yeah,
Okay,
Manan.
sir. Okay, okay, sir. So yeah, if you can even see that since we changed the sample time from 0 to zero point 0.1, the signal also seems to change. So again, I'll change it back to 0, and you can see that. Yeah, so it is again back to a continuous kind of signal back, and then I'll again hit run, and you'll see that you get this. Also, like if you can see that uh, this does not look very continuous in that way. So what we can do is we can go in this tab modeling and change some system settings, right? So in the solver, I'll go and make max step size to 0.01 maybe, and then hit apply. Okay, and in the simulation tab again, I'll go and hit run. So if you can see that the graph looks much more smoother now. So since we changed the maximum step size from auto to zero point zero 0.01, you can see that we get a much smoother graph now. So I hope you're able to follow me. So yeah, what if I want to add much more, add some more things, right? So maybe we'll start with like adding much more elements to this. So yeah, you can actually drag the connections the way you want. All you just need to do is tap this and move uh, the connections wherever you want. So yeah, maybe what we can do is there is an option of commenting out. So I can comment out this signal maybe, and if you want, you can also remove the connection from this, so that just like in a code, when we uh, comment out a line, we can actually reuse. So we do it so that we can reuse it later on. So maybe if you feel that there is an element which you feel that you may use it later but you don't need it right now, you can comment it out directly by tapping it. And if you can see that there is a percentage sign which shows that it is commented out, and it also fades out actually. So yeah, what if I want to add a transfer function to it? So suppose I want to add a transfer function. All I can just do is double tap again and look for transfer function, and maybe I'll expand it. So this is a first order system. So if you guys remember your controls classes, this is a first order system, and I'll again connect these connections. I'll again add the connections and see if the transfer see if the value that I'm getting is like how does it change. I'll again hit the run button, and you'll see that my input signal is a 3 amplitude blue sine function, and the first order is trying to catch up with the uh, with my actually the input signal. So sine wave may not be a good uh, good signal, a reference signal to start maybe. So what I'll do is I'll maybe use a step function. So I'll again double tap it, right step, and create a step signal. Again, I'll remove the connection here and comment it out. Or maybe if you want, you can delete it. So this is a step signal, right? And again, I'll tap here and set the uh, change the settings a bit. So currently we have a step for a step time of 1. So it will have a step input at 1 second. Mail, I'll change it to 4 seconds. So it will go up at 4 seconds, and the final initial value is 0, and final value is, so maybe I'll just do it 3 times, since I already used 3 as amplitude earlier, and hit apply and okay. Then I'll run the simulation again and see what does my output looks like. So my output looks something like this. So this is a step function. This is a step at 4 seconds, if you can see it. And my first order system tries to again track this system. So there are some delays, but it is able to get close to the reference signal quite. It is able to do it in within what? Uh, so I guess somewhere between, so to say, 12 seconds. And the signal started at 4 seconds. So I think 8 seconds it took almost. So what if we want to use a different transfer function, right? So you can also double tap this transfer function and try to change the values maybe. So suppose if I want it to be a first order with some different coefficients, suppose this. So you can see that we have changed this transfer function to 3s plus 1. What if I want to increase the order of the system? So this is a first order system right now. Maybe we want to make it a second order system. So I'll again add we I can just directly add one in the starting and hit apply. So you can see that this transfer function has changed from a single order system to a second order system. All you can do is you can keep on adding more elements and increase the order of the denominator. In a similar way, you can add the order in the numerator as well. So so basically you can change the order of the numerator as well as denominator. So I'll again change it back to say second order system as of now, right? And hit apply. So let's see what the output of this is. This looks like. Yeah, hit scope. So yeah, if you see it is it starts a bit slowly and then it tries to catch up. So it takes a bit longer as compared to a single order system to again track the reference signal, right? So what should we do to maybe make it much more faster? So generally uh, we can use feedback loop and some kind of controller to maybe uh, get it uh, get the get it to achieve the reference signal faster, right? So or what will happen if I just add a feedback loop maybe here. So or what I can do is search for a block called sum, right? And I'll get this block in which I can add or subtract the signals. So if you can see that we have two plus signs, but generally for we do have a negative feedback in our system. So what I'll do is I'll change the signs from plus plus to plus minus maybe, and then hit apply. So you can see that like we have a negative we can add a negative feedback to this. And I'll just again yeah connect all the links and also try to pull out negative feedback from this. And yeah, so we are done. So if I pull it back, and I'm assuming that I'm able to, so my signal from my sensor is able to get the output signal clearly without any lags or any disturbances. And again, I'll just run it and see that uh, like the output has changed. Although the signal is able to get to a stable state earlier now, but my uh, my signal has almost halved actually to what I actually want. So it is converging to 1.5 amplitude as compared to 3. So maybe yeah, we'll have to add some kind of controllers uh, to it. So a simple controller which we can think of is maybe a proportional controller. So if you guys can see that we have a signal which is almost right, but the problem is that it is actually halved in that way. So we can use some kind of controllers. So I'll just start with a basic controller which generally comes to our mind is using a proportional controller. So I'll add a gain block, maybe gain here, and yeah, place it here, and then change the gain value to maybe say, so since we see that it is half, let's try with a gain of 2, right, and see what happens. And I'll name it name this controller as P. So if you remember your controls lectures again, you can recognize that this system is a plant. This transfer function basically signifies our shows our plant model. So plant is a second order plant model. Then we have a proportional controller and a feedback, a negative feedback with exact, like we know the we are able to sense the signal as it is. So yeah, I'll again hit the run button and see if I am getting somewhat better results. So yeah, if you are able to see, I'm getting a bit better result as compared to last time. So last time my signal was at 1.5. Now it is more closer to my reference signal of 3. So all I can do is I can maybe try and increase this further. So to say 10, and then again hit apply, okay, and run the signal again. Right. So if you see that there is some kind of overshoot, and then there is basically there is a transient phase, and then it settles to says I guess 2.7, 2.8 something, and but still there is an offset, so you can go on increasing the uh, gains of this. Then so if you now know that we can maybe add a derivative block or integral block. So we can
Excuse me,
actually,
Manoj.
yeah.
Sorry to interrupt you, but you can do one thing. Just go in the scope. You can actually see the signal specifications. Just go to the scope. Just open a view or tools. No, the tools. Sorry, just open the tools. Sorry, the not the view tab, the tool tab. There are measurements at the last.
Yeah. So you can actually measure the signals at the last. So you can actually put two time, like a starting time frame and the end time frame, and maybe measure the signals at this point. So at point 2, the plant signal which is in yellow, you can see that at this 22.5 seconds, the value of this is 2.727. So you can actually measure the signals output at this point. And if you want to check the step signal which we already applied, so we already know that it is a constant 3 at this point. But still, if my signal is say a sine wave or some other kind of signal, I can also measure all different signals here actually. So I can go on and click this drop down menu and select what signal I want to measure. And so currently step signal, and then I can have a starting time and an end time, so that I can measure the signals at different times. So if you want, I can just also directly change it to 20, and maybe see, so we are able to see that the transient phase is almost dying out at say 8 seconds. So yeah, if you see that, sorry, I should change it to plant. So yeah, if you see that the difference between these two signals is quite less, so we generally have some kind of errors in our mind, so that we can actually uh, like measure how different, like when the transient phase is kind of dying out. Uh, so it is quite near to our dying out transient phase. So I guess it is somewhere here maybe when we are getting a constant kind of signal. But yeah, still there is some kind of offset. So we'll have to add uh, different. I'll also add different elements to it maybe. So
Sorry to interrupt. Yeah,
yeah,
I hope all the students who are attending this session are familiar with control theory. Okay, so uh, in case you haven't studied control, then you probably will not be able to appreciate what is going on. But if you had a course in control in your BTech, then it's a very good example. Okay, so Manan, just a couple of points. To start with, when you took the amplifier gain as one, the plant that you have chosen is actually an overdamped plant. Okay, so that's why we got the response that we actually saw. So once we added a gain, so what was the value of the gain that you gain? So now the properties of the plant actually, I mean, if you evaluate the closed loop transfer function, that will probably indicate that the system is uh, now underdamped. Okay, so you can perhaps change these step signal to start at t equal to 0, and let's see what happens then. And let's the only that is the only let's start with that change first, and let's see what happens. Okay, so if I
in the step signal, sir.
yeah, the step signal, the initial value is the step time is
4 seconds right now.
4 seconds. So this is the time for which the step acts. So can I have the step function which starts at t equal to 0?
Yeah, sure, sir.
Yeah. So now let's see what happens now.
Yeah, it is just a shifted kind of signal now.
Yeah.
So it will start at 0 and you'll have a step from the 0 seconds itself.
We have oscillatory behavior. Okay.
Yes,
So
yes.
it eventually settles down, but we have a permanent offset. Okay. So uh, generally with a second order system, there is a permanent. This something seems to be contrary to what I sort of think. Does it change the order of the plant?
No, so actually, when you bring in the closed loop, there comes a steady state error when you bring in closed loop to the system itself.
Yeah,
And that's what until if unless we because it doesn't have a pole at 0, so its error won't completely vanish. So unless we introduce an integral controller, we'll have to increase gains to really large values and introduce really large oscillations if we want to get the steady state error to really minimal values, but it still won't vanish completely.
so if you have an open loop first or second order system, it will have a zero steady state error.
Yes, sir.
Okay. So
Yes.
that we have used a controller, a proportional controller, we have some finite steady state DC oscillator error.
Yes, sir.
Okay. So can we change the amplifier gain to, let's say, 100?
Yeah, sure, sir. So if I change it to say 100 and then hit apply, run it again, we'll see that although the steady state error has decreased now, but the oscillations have increased quite a lot.
Yeah. So we have the initial transients. Yeah. Fair,
So
fair enough.
it
So
goes up
I,
to
I
almost 60% kind of.
yeah. So I hope the students who are listening appreciate this kind of a thing. Okay. Please go ahead, Manan. Yeah. Thank you very
Okay.
much. This is a good example. Okay. So let's move on.
So yeah, if you see that we have different elements now. So what we can do is, if you want to, if we are working on on some say real time uh, project, and we want to, so things which we want to basically model as of now, maybe, so we can actually model a plant or a controller. So work of a robotics engineer might be in these two areas, to maybe develop a controller, or maybe and for developing a controller sometimes we do need a model of a plant, right? So if you want to tune the parameters of this controller, say PID controller, I should have some decent enough approximation of how my plant looks. So currently this is a second order system. So what will happen if I have some example. Maybe we can model a DC motor in Simulink. You can start with this simple DC motor kind of model. So if you see that these are the governing equations of a basic DC motor, where V is the voltage, input voltage, K is the back EMF of the like it is a constant, motor constant basically. So and omega is the angular velocity of the motor, I is the current, R is basically the resistance of the. So I should have actually put a model as well. uh, okay. So and again then we have in inductance L, and the rate of change of velocity, rate of change of current basically. So my input voltage is equal. So let us let us assume that these equations are correct. Again these again T is basically load, external load. So it will be measured in terms of torque, external load. Then again we have this constant K, motor constant. Then there is some kind of uh, the coefficient of friction basically. If my motor goes on at a higher speed, will have some kind of friction, viscous friction basically. J is basically the inertia, and this is the rate of change of velocity, which is angular acceleration actually. So if I actually rearrange these terms, we'll see that uh, we have this. We will be able to see that my di by dt looks equal to this, right? And then if we integrate it, I'll be able to get my input I, and in a similar way, I can rearrange the terms here and get my omega, which is uh, angular velocity actually. So what we'll do is we'll just start with putting some values for these terms actually. So I'll put my inertia 0.01, viscous friction coefficient as 0.1, and all these things, and try to make a basically a block diagram for this simple DC motor model, and try to make this model. So yeah, again I'll maybe delete these things again, and again I'll start with a basic kind of flowchart. And before that, what I'll do is go in the MATLAB command window, and try to put these values first, so that we can use these variables, and if we can directly use these variable names in the Simulink models directly, right? So if I want to change these models and then see what is the effect exactly uh, on different parameters, we can actually do this directly. Sorry, excuse me. So I'll start with again step signal um, for my voltage. So yeah, yeah, sure. Is there any doubt? Okay, okay. I thought someone asked something. So I'll put a step function voltage. So this block signifies my voltage. I can maybe change the values. So it will step at one, and the final value maybe 5 volts, and hit apply. Okay, and then we have You see, then we have actually so we'll use two integrations actually now. So one is for the current and one is uh, for this angular velocity. So I'll try to keep it a bit slow so that I can actually explain each and every step, right? So first of all, what all elements do we have as inputs? So we have voltage as input. So basically, in a motor, if you see what is an input, we have we apply some kind of potential difference to the motor, and we get rotations or some in a DC motor, we have some kind of velocity with which the motor actually rotates. So we have omega as our output, right? In radians per seconds or rotations per minute, RPM, whatever is the unit that you prefer. So basically V is the input and omega is the output. So I'll add a scope maybe so that I can measure the output, which is rotations per second, radians per second, and I'll bring out a signal out of this and maybe label it. Do I label it? Okay, yeah. So we have voltage which is coming out of this. So if you see what are the equations, first of all, so we have we do need a omega, we need a current, but current is what we want from the output as well. So we'll have to use some kind of integrator block, right? So does any one of you know what an integration block looks like? So what is the transfer function for integration? Anyone? Okay, so an integrator looks something has a transfer function of 1 by s actually. So if you have studied control theory, you might have learned that an integrator has a transfer function of 1 by s. So you can either search it directly as integrator, and you can get a transfer function of 1 by s directly, or what we can do is search for transfer function and then change it to 1 bias instead of just in a similar way how we did actually for changing the system from first order to second order. You can also change it from 1 by s plus 1 to 1 by s directly. Okay, so we have this integrator block here. Then so basically what my integrator block will do, it will try to take so it will take this di by dt, and if I integrate di by dt, I get I directly. So my output, or what should my output of the integrator be? It should be a signal I, right? uh, are there any doubts? Okay, if there aren't, I'll continue. So the other blocks are that we will actually need omega, which I have already taken out a signal for omega here. So I'll again add a integrator. If you see, so my omega also requires an integrator finally. So this is what you generally do when we want to make a plant model from say from different equations. You want to transfer it to control systems blocks. Basically, we take each and every element, and then we compile it in a whole so that we get some kind of flow chart. So I'll again add an integrator. Right, so it might look a bit off right now since we don't have a basic structure, but once you see that we have a basic structure, everything will start coming together. So this signal is omega signal. So how do I add a name to this? So this is,
Double click on the arrow. You'll get the name.
yeah. So since I don't have an omega signal, I'm just adding a W here, and in a very similar way, if I double click it, I'll get a I current, which is current actually. So maybe I'll zoom it a bit. So you can zoom in and zoom out using scroll of your mouse. So I hope you are able to see this signal I and signal omega, right? So if I see my uh, equations again, for like getting, so the input inside my integrator is basic, it does look something like this. So it is basically a gain block of 1 by L, which is taken from a sum, or maybe using voltage, a sum of voltage scale times scaled uh, angular velocity, and then again scaled current actually. So the current is multiplied by a resistance, and then it is subtracted, so we'll use a negative addition here. Then we have uh, k times angular velocity, and again it is multiplied by a uh, negative one, and then we directly add a voltage, the output of this voltage block. So I'll add some block here, and increase the size here, and yeah, I'll have to change the sequence of signs here. So my first will be negative, then I want to take a voltage which is directly added, so a plus sign for voltage, and again a negative sign for this from the output from the angular velocity directly, and then I'll hit apply. Okay, and I'll take it and add directly the voltage signal, and take some kind of negative signal for the current, and add a gain block, right? So if I use um, control I can flip it. So control I for flipping it. Okay, and directly add this here, and take this input from the current, which I'm getting from the integrator basically, and again I want a negative uh, contribution from a scaled version of my angular velocity. Again I'll do control I to flip it, and connect these blocks, and take an input from this angular velocity here, right? And then what I'll get is this part basically, without the scaled 1 by L, I'm able to get V minus. So currently I've put K and R is 1, but I'll define these variables first in the MATLAB, and then I'll directly use them here. So uh, currently we have V minus omega minus I, if you can see here. So I'm taking negative I here, negative omega here, and adding a voltage to it, right? And since I just want to use these variables, first of all, what I'll do is define the variables, the values of these variables in the MATLAB command window first. So I'll just put these two files in parallel. I'll what I'll do is put j equal to 0.01, b equals to zero point 0.1, A equal to 0.01 again, R equals to 1, and L equals to 0.5. We we already have V voltage actually, and if we actually want, I can also change V, but since I already have that, I'll prefer not to add this, and external load as maybe zero point 0.1. Okay, and so now if you see in my workspace, I have the values of these uh, B, J, all these variables stored in these variable names, and I can directly use these variable names in my gain blocks now. Okay, so if I change my gain here, so since I'm getting this, I'm attaching this gain block to current, so we'll have variable R here, right? And then hit apply and okay. In a similar way, we are using a gain of K along with, sorry, a gain of K along with this, along with the angular velocity. So I'm putting a gain K here. And now I'll again use a gain block for this 1 by L actually. If you see, I have multiplied a gain of 1 by L to this. So this basically, so if you see, this basically looks my like my di by dt term, right? So I can directly add a gain block here, and my gain is 1 divided by L. I'll use this value of L, apply again, and okay, and connect my uh, gain block to this. So this signal is my di by dt, right? So di by dt. Cool. So now, if you are able to appreciate this, we have made blocks of we have used different blocks which we have studied till now to make to get current out of uh, current using my equations actually, and I'll again put it back. So I have used these two equations. So first, I've currently used the first equation to get current as my output using my uh, using these sets of blocks. But now I'll have question that I'll also have to make a similar block as a system of blocks for our angular velocity, which is our main output actually. So if I bring this integrator, shift this integrator a bit, and again see the equations. So I'll again have to rearrange these terms so that I get rate of change of angular velocity, scale it, uh, take these, add these components, and then scale it by 1 by j so that I get d omega by dt, and then use an integrator to basically get my final output, right? So we have to use different terms like scaled version of current, negative scaled version of rate angular velocity, and a negative load actually. So I'll again add some gain blocks here. Control I to flip it and take input from this. Add again a sum block, and again I can change the list of signs here. So negative, positive, negative, apply, okay, and add it here. In a similar way, I'll use a gain block for scaling my current here. right? And bring these, connect these arrows, and I have to use some kind of constant uh, kind of load, since our load currently is constant. Again, control I to flip it, and I'll rename it as code. And have I defined my t? Yeah, I have defined it, so I can directly use the value as t here. Okay, and add it directly here, right? So I hope everyone is getting what I'm doing right now, right? So, and then again connect these, connect this with the. So currently what I'm able to get is this block scale times k scaled, I've scaled I by k, omega by negative b, and added like subtracted a load actually. So it looks something like this. Oh, I've actually not added a gain here. So this gain is negative. So I have a negative block here. So I need not add a negative b. So just I've added a b here. In a similar way, I have to add small k here, apply, and then OK, right? So I'll again add a gain block. So this gain will be 1 by j, as we did for 1 by l, right? I'll again use a 1 by j here, apply OK, and put it here. And then again connect this to the integrator. So if you see, we have a signal of uh, d omega by dt here, and I'm integrating this. So if I show the equations again, so my d omega by dt looks something like 1 by j. So this is the gain. Then I've added current, subtracted omega, and subtracted load. So this completes my flow chart as of now. So what I'll do is I've actually given a step input of voltage here, right? 5 volts here, and the step time is 1 second. So let's see what my current values are outputting. So this will output my omega. I also add a voltage in this. So if I bring my cursor close to the boundary of this, there appears a plus sign. I'll add this plus and add one more output which I want to measure, which is basically the voltage on the very same graph, right? I'll name this signal maybe V. Okay, this is already omega. Try to make it as looks as simple as possible, and then run the simulation. So if you see that the output looks something like this. I don't know why in the negative direction. Maybe since we have used some values which are in the, so if I apply a positive voltage, I'll get some kind of negative uh, angular velocity. So it will so negative angular velocity means it will rotate in the other direction, right? So it will first go till -1, and then again continue back. There is some kind of transient at first, and then it will settle at uh, at zero point 0.5, I guess. So again, I'll measure the values for omega and v actually. So if I see my v is constantly 5 at each point, and my omega at different times is negative zero point 0.5, right? So if I go here, it will first, there will be a transient which actually makes it negative 1 at first, and then since we have a step function at 1 seconds, so yeah, this zero voltage will actually put it to a negative 1 kind of uh, thing, because I think we have this load here first, but this shouldn't happen. So this might be uh, glitch maybe. So I'll change the stepping time to 0 maybe, and then again run. So if you now see that it will first try to go in the negative direction, but my so when I apply this voltage at 0 seconds, it will again just try to get back at uh, to some kind of constant negative zero point 0.5 actually. So whatever the stepping time I keep, my final constant angular velocity will be at negative zero point 0.5. Okay, so you can actually play around with these things, with these parameters actually.
Yeah,
uh,
Manan.
yes sir.
Yeah, try to put the load torque as load 0.
Yeah,
Which
sure sir. So if I put my load, okay, I've already put it there. So I'll change my, yeah, I'll change my load as 0 right now, and again run the simulation. So I'll see that since my load is 0 now, uh, it will just try to uh, like follow the direction of velocity. So what my load was doing, it was trying to reduce the uh, reduce my actually the omega. So it was putting an external negative torque actually, right? So so generally when my torque, if I put an external torque, it is more like a resistance that I have to overcome rather than an external torque maybe. Sometimes it is an external torque, and sometimes it is more like a resistance, but I think we have already accounted for the resistance, I guess. Yeah, so I've already accounted for the resistance in this. So this external torque may be due to some external factors, maybe so it is trying to make the motor rotate in some other direction. So this external torque basically tries to account for that external load, which will be in a different direction as that of my voltage. So again, if I change my external torque to zero point 0.1, and then I'll have to increase the voltage, so that, so let's see how my, or maybe I'll try to reduce the external torque this time. So I'll keep it 0.01 instead of zero point 0.1, and I'll again run the simulation and see if my, yeah, so if you see that initially my uh, I hope you guys are able to see it. Initially, my angular velocity tries to go in a negative direction first. So if you see the output of the first measurement here, it is negative 0.0185, but then the voltage is high enough to make it rotate in a positive direction, in the direction of the top, in the direction of the applied voltage actually.
can you
So it
the
becomes
region
positive later on.
0?
Yes sir. So actually we can play around with these variable values and see how these things actually affect our uh, uh, final signals actually. So again, if I put my torque value as 0.1, and then I'll have to increase my voltage actually. So here I guess my voltage value is less. So I'll try to make it 10 volts maybe. Hit apply. Okay. And sorry, I'll run it. So yeah, if you see that 10 volts is exactly exactly the value which is able to just make it like it will just counter the external torque, this external torque of point 0.1 actually. So if I want a signal, if I want to make it rotate and overcome this external torque, I'll have to apply more voltage, right? Or yeah, so I either have to find ways to maybe reduce or change some values, but generally we cannot change the motor values once we already have a motor. So all we can do is maybe try either to reduce the external load torque, or maybe try to increase the voltage depending on the voltage values of the applicable values of motor voltage that we can apply, right? So if you see that yeah, actually you can actually play around with these values of different motor constants, and actually use these values to maybe if you want to uh, decide a motor first, right? So we'll have to model a plant first. So this model of the plant will actually so if we model this plant and you want to use certain types of motors, right? So you can actually decide what motors to buy depending on the plant values that you actually need, right? So this is how we actually model the plant. And then if I actually want to compress all of this into one block, what I'll do is I'll create a subsystem. So my subsystem looks something like this. And if I click this subsystem, I'll get this flowchart again. So I can actually make my model much more neater actually. So I'll again rename this subsystem to my DC motor model, DC motor, which is basically my plant, right? And then maybe add a some block, right? And then take a negative feedback and put some kind of controller. So currently I'll just put a gain block. Right? So my closed loop. So if I don't add a negative feedback, this will be my uh, open loop system. So the values that you have seen till now are the values of open loop controllers actually. So this will not be voltage in that case. I'll remove this. It will be a reference which will be in terms of the output actually. So it will be the reference will be in terms of omega actually. So I can actually make a open loop I can actually make an open loop system in this way. So I'll give a step input in terms of reference omega, right? So this thing will be omega underscore ref maybe, and this will be my output omega omega out. Yeah. So This is how my open loop system looks. And if I add a negative feedback, this will make it a closed loop system. And then we can actually, so now that we have made a plant model, now, so the next job of a robotics engineer will be to maybe develop a controller for this model, right? So maybe I think it is 11:30 now. So maybe in the next lecture, we'll see how we can actually make a controller, design a controller, and tune the parameters for that controller, and so that we get a good output, right? So I'll run this system once again, just for the sake of completeness, right? So if you see that my reference signal now was just one, and my output is in negative direction again. So we'll have to actually so since my gain block is just one, so I didn't and actually expected it to work. Maybe I'll put it 100 and see just if it is making it positive. Yeah, so it is able to somewhat track with this proportional controller. But in the next lecture, we'll see what all different like elements that we have in the PID controller. So we have an integrator, we have a derivative. So we'll study basically what each and every part of this controller does, PID controller does, and see its effects in the final uh, output of the signal actually. So yeah, so if you have any doubts, now you can ask me. Now I think is a good time to ask these doubts.
Anyone? Okay, Manan, you probably need to look at the equations again.
Okay, okay, sure, sir.
Yeah, so take a look at the equations, see whether they have been derived correctly, and then probably we'll get a more expected output from the simulation.
Yeah, sure, sir. I'll look it again, and even the students they can actually try to model different models, maybe motor, DC motor, or something else. So a DC motor is a simple example which I actually wanted to start with. So we'll actually so you guys maybe take it as a assignment or something. Go and look for some equations, try to build these models and play around with the Simulink uh, Simulink more actually, so that you get some you get your hands dirty with the software and become much more fluent while using it. So, so I think there was a hand, like there was some question from someone. Okay, okay. So, Sadik actually, sir, is asking which control course should he follow so that he is able to catch up with the controls part. So,
Sorry, which control?
so Sadik actually hasn't done a controls course as actually. He has a question which topics. So like you can actually go through some basic building blocks of controls. Uh, like just in a way, like I have developed a flow chart, controls flow chart out of equations. So maybe this skill is what you will require actually. So suppose if you have a set of equations, how do we have like how a transfer function looks, and how what impact does it have on the final output of the signal. So maybe that will be helpful, I guess. So sir, do you have some courses or some online material in mind so that people who don't have some background in controls, maybe they will have some.
See, I mean, most of the students who are enrolled in this course are not from NIT. So some of them may not have taken a course in their BTech, or if they have taken a course, they probably would have, because they've been out of touch for some time, so they would have forgotten it. So it's not because control systems is a full-fledged course, so it requires some learning. Okay, but then the course that we are actually, the robot mechanics course, this is just these tutorials are just to illustrate the basics of Simulink. So even if you don't understand control concepts, you still learn how to use Simulink and model equations. You can see effectively, if you see what Manan has done is that he has a set of equations and he has modeled them in Simulink. Okay, with very little control theory. Okay, though interpretation of the results does require some amount of understanding of control theory, but precisely he has what he has done is that he has modeled the two equations that you have seen. One equation for the current and the other for angular velocity. He has modeled them in Simulink. So if you take it as an exercise in modeling, then it's okay. You don't really need control concepts. And in this course, because we'll be focusing on robot mechanics, so control probably hopefully we'll take control of robots in next semester. There I'll probably sort of teach a little bit of control, and then we can sort of appreciate things better. But if you take if you read the book by Norman Nice, okay, yeah. So who was the person who was asking this question?
I guess Sadik Radu.
Sadik. Yeah, Sadik. So if you sort of if you can get hold of Norman Nice, okay, maybe Sohaib can help you get a hold of a copy of Norman Nice, and you can start reading a little bit, you know. So, and in case you need any help, you can always ask me in the class. I can explain the concepts of control to you, what we are exactly doing. Okay, so probably a little bit of reading on your part, and some questions that you may ask in the classroom will help you get along. Okay, so if there are no further questions, I think we'll call it a day. Okay. So thank you, Rajpal. Thank you, Manan. Manan, are you Rajpal's batchmate, or
Yeah, so actually Rajpal is my senior actually, sir.
So and you are enrolled in which department?
I am in actually there is a department called Cyber Physical Systems here.
Cyber, which it's a part of mechanical department, or
So it is a separate department actually. It is a interdisciplinary department in the field of robotics actually.
who
So
is the
people, yeah, so people who, so my BTech background is in mechanical engineering. So I did my BTech from IIT Bombay in mechanical engineering, and then I did started my PhD directly after my BTech.
So who is the chairman of this cyber physical systems department?
So Professor Bhardaj Amrutar, he is the chairman of the department.
Okay, fine, fair enough. So there is a Robert Bosch Center for robotics as well.
Yes, sir. Yes, sir. So this is the very same center actually, Robert Bosch Center for Cyber Physical Systems.
Okay, fair enough. Okay, thank you, Manan. Thank you very much. Thank you, Rajpal. Okay, I mean, I really appreciated the session. Of course, the results were a bit sort of unexpected, but anyway, so some amount of learning, or good amount of learning, was initiated. I hope the students appreciate what we have learned in this class. Of course, I mean, learning any skill, any skill like Simulink or MATLAB, or for that matter, any other uh, technique or skill, it requires some effort on your part. So, as Manan said, you need to sit on your systems and play around with Simulink. Okay, play around with some basic equations and see if you can simulate a simple spring mass dashboard system. The equation is well known. Okay, and you can give it various inputs, and you can, and the output is also expected. Okay, if I have a spring mass dashboard system and I give, say, a step input, I know what the output should look like. If I give it a sinusoidal input or a ramp input, I know what the output should look like. So if you play around with such systems, such basic systems, you'll be able to appreciate Simulink in a better way. So as you can see, it's a very useful tool. simulation. So hopefully in the next sessions we'll probably go for position control and this speed control of a DC motor. Okay. So thank you, Manan. Okay. So we
Okay.
hope to see you on Saturday again.
Yes, sir. Sure.
Yeah. Okay. So I'll call it a day. Thank you very much.
Okay. I'll stop the recording and